If you remember, with this notation, we describe this group. It's what we call the general linear group of size n with real coefficients. It's just the set of all square matrices of size n by n, right, of real coefficients, which are regular. So in other words, whose determinant is not zero. All right. Okay, the determinant precisely is a function that maps this group. So it takes any matrix here, right, any matrix A here, and maps it to this other group, which we call R times. And it's nothing but the group of real numbers, non-zero real numbers, with respect to multiplication. So the mapping is, the mapping is, you take the matrix and you calculate the determinant of this matrix, right? And that is the image of this matrix here. The determinant is non-zero, so it belongs to this set here, okay? And this here is a group, right? Okay. This, of course, is determinant is a surjective mapping. So the image of the group, so the range of this is just R times, because any non-zero real number is the image of some matrix here, right? It's very easy to realize that, because you just take x, which is any non-zero number, a non-zero real number. You can easily construct a matrix whose determinant is x. You just take x, 1, 1, and 1's in the diagonal and zeros of the diagonal. The determinant of this matrix is equal to x. So this is a surjective mapping. It's not only that, it's just it's a homomorphism. And that is very easy to prove, because homomorphism, remember, maps the product into the product. So the product of this group into the product of this group. And that is exactly one of the properties of the determinant. If you calculate the determinant of the product of two matrices, that is equal to the product of the determinants of the two matrices. So this is precisely the property that tells us that that the determinant, this function, is a homomorphism. However, if n is larger than 1, so n equal to 1 would be just real numbers, okay? But if n is larger than 1, so not real numbers, just matrices, okay, then this is not an isomorphism. And it's not an isomorphism because different matrices can have the same determinant, right? Well, it's easy to see, but just as an example, this matrix here has the determinant A, but also this matrix here, B, which may be equal to, I don't know, maybe square root x here, 1 to 1, if this is, if x is positive, okay, or if x is negative, you can say that b would be the square root of absolute value of x, and negative the square root of absolute value of x, and then 1's in the diagonal, and then 0's here. So you see, you can construct easily different matrices, and these are trivial constructions, but you can make even more complicated constructions. Doesn't matter, because what this proves is that there are different matrices having the same determinant, right? So the mapping is not injective, and therefore it cannot be an isomorphism. Finally, the last thing we need to do is to calculate what is the kernel of this mapping of the determinant. And as you remember, this is by definition the set of matrices or sets of elements in the first group, in this case matrices, square matrices of size n with real coefficients, whose determinant, so that map into the neutral element of the second group. The neutral element of the second group is 1, so the determinant must be 1. And this is a same as this one is a group that has a name. This is a general linear group of size n of real coefficients, right? This one also has a name because it's a very important subgroup of this one, and it's called the special linear group of n elements, well, of size n, with real coefficients.